Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at some basic definitions which we are going to come across, especially concerning the transition elements. And these are going to assist us distinguish between the basic definitions and the IUPAC definition of transition elements. Now, in our various discussion on this particular section of the periodic table, we are going to come across particular characteristics which are going to be associated with transition elements. Now that one, of course, is going to require us to understand the concept of various electronic configurations of these basic elements. Of course, we have done an exclusive video on how we can allocate electronic configuration for various elements, and particularly the orbital diagram, which I've done in an exclusive video. So I'm going to put a link of that one in our description box, so that in case we need to do a revisit, it will be okay for us. So in this particular discussion, then therefore I'm going to start from the particular classification which we had put in the periodic table. Now, I said that the periodic table can basically be divided according to the position of the electrons which are going to be present in the valence shells. And in this particular case, given a particular definition for the S and the P block elements. So if an electron is going to occupy the last or enters the valence shell, then these elements are going to be regarded as the main group elements. And these, of course, are elements, as I've said, which are whose electrons, so whose last electron occupies or occupy valence shells. Or a valence shell. So in this case, I've defined basically the concept of a valence shell. These are shells which are constituting the S and the P orbitals, which are going to constitute this last electron. Now, we had basically defined the S and P block elements in our previous discussion, where we said that when the last electron added enters the valence shell, then therefore these are going to be classified as a S or a P element. So we had given specific examples for the particular elements that fall under this particular category, and of course those ones included the alkali metals, the alkaline earth metals, and of course for the P block elements, those ones are the group 3 or the way to group 8, as we had mentioned. So in this particular case, we're going to look at this second example, which are basically the P block elements, and try to distinguish them from the above, which we have defined as a group of elements whose last electrons are going to be occupying this valency, of course, shell. Now, in that particular case, then therefore we're going to look at, so we can just have this one as valency shell, given as such. So in this particular case, the second type is going to constitute the D block elements, and these are elements whose electrons are going to enter the D subshell in the next to the last. So we have defined basically the concept of an n-1 in our various quantum numbers. So for various subshells, we are going to have this specific block of elements of the D block having the last electron enter the D subshell, which is basically the next to the last shell, which is going to be forming the last part. So we shall give this one using various examples. And these are going to be regarded as transition elements. And then we said that among these transition elements, there's an integral part of this one, which is going to be forming on a third part. But of course, these F block elements are going to be an integral part of the D block elements, although I'm going to mention them as a third category, so that in case we need to distinguish between the two, then it's going to be easier for us. So the third type of the D block, the F block elements are going to be the type of elements whose last electron is going to enter the F, or this particular the subshells. So this is going to enter the F subshell, and in this particular case, then therefore we're going to see that this F subshell is going to be in the n-2, of course, a shell, which is the second shell below the valence shell, and these elements are going to be given the name of the inner transition elements. So for the first case, which we had regarded as the D block, so basically these are going to be outer transition elements given as such, and then for the F, those ones with the whose last electron is going to be occupying the F subshell are going to be regarded as the inner transition elements. Perhaps this ones is going to be, these specific definitions are going to be particularly elaborate when we are going to give our specific examples. So let me try to give basically a few of the elements which we are going to come across, and then we'll identify them whether they are either transition elements or not. So I'm going to use a few rules which we have discussed in our various videos. So among them, I'm going to use the 3 basic rules of assigning the orbital diagram and the electron configuration. So these basically are the Hans rule, the Pauli's exclusion principle, and then lastly I'm going to look at the Aufbau or the building up principle given as such. So in this case, these 3 basic rules for construction of the orbital diagrams and electron configuration are going to assist us in understanding the overall concept of the electron configuration, and how we can use that one in identifying the last electrons occupying a particular subshell in various elements, or in terms of their electronic configuration. So I look at the concept of zinc, and then we shall look at perhaps cadmium, and then we shall look at mercury. So these elements are going to assist us in trying to define this specific concept of of course, transition elements. Now in this case, I'll use the building up concept, whereby we say that if we have this particular element, so this one consists of an atomic number of 30, and then this one consists of an atomic number of 48 and 80, or they have the atomic numbers of 30, 48, and 80 respectively. So I'd said that we are going to use a shorthand notation in trying to assign electronic configuration for various elements of the periodic table. And this constituted the use of noble gases in trying to give these particular elements their electronic configuration. So for us to find the electronic configuration of the above elements, we are going to use these noble gas elements, which I'm going also to list together with the atomic number. So we shall have neon having 10, and then we are going to have a krypton. Of course, this is going to be argon. Argon is going to have 18. Then we shall have krypton having this one of 36. And then perhaps we shall have xenon having 54. So in this particular case, these are going to be elements which are going to assist us in trying to assign a shorthand forms of this specific configuration. Now in this case, sorry for that, I'll use the particular the of course the building up principle in trying to assign electrons, whereby we say that electrons are going to occupy the lowest orbital available in terms of energy levels. So we're going to have 1, 2, 3, 4, 5, 6, 7. So these are the various levels for the subshells or the shells which I'm going to assign. So I'm going to have 2, 3, 4, 5, 6, 7, and I shall have 3, 4, 5, and this is going to be 6 and 4, 5 respectively. So these are going to be the respective column in identifying the lowest energy levels in terms of ascending energy. So we shall have the first column is going to constitute the S subshells, and then we're going to have the B given as such, and then we're going to have the D for the third column, and F for the fourth column in that particular order. So for me to find the number of course, maximum electrons which are going to occupy these various subshells, I'm going to, of course, give this one in terms of our last discussion. So we have said that the S subshell is going to consist of a maximum of 2 electrons. The P subshell is going to be having 3 orbitals, which a single orbital is going to have a maximum of 2 electrons, so it's going to have a maximum of 6. And then we're going to have the D orbital having, the D subshell having 5 orbitals, so it's going to have a maximum of 10 electrons, 2 for each. And then for the F subshell, it's going to constitute over 14 electrons in that specific case. So for me to have an easy way of trying to achieve this one, I'm going to assign this one 2 electrons for the maximum number of electrons for this specific. So this is just going to be a technique that I'm going to use for this particular discussion. So we shall have for the p orbitals having a maximum of 6, and then we shall have the d orbitals having 10, and then we shall have these f orbitals or these f subshell having 14 in this particular case. So according to this specific principles, we're going to have this specific energies ascending in this particular order, following these arrows over the strokes which I'm giving on the board. So we shall have these ones arrows moving in this specific direction in forms of ascending energy from the lowest to the highest one. So in order for us to try and identify what are the various configurations of these particular elements, we're going to have these orbitals ascending in this particular order. So the first one, 1s2, 2s2, and then we shall have these ones going in that particular order. So at a specific point whereby we're going to have this configuration of the noble gases, we're going to have that one given in terms of square brackets, and then we shall have the remaining orbitals which are going to be of course filling up the remaining amount of electrons for this particular case. So in case we had of course a configuration for zinc, then therefore we're going to have that one assigned as a noble gas element, which is of course going to be preceding that specific element, and that is going to be argon. So the difference between the numbers of electron for argon, which is 18, and of course zinc is 12. So in this particular case, then therefore we're going to fill the remaining orbitals of this specific configuration according to the energy levels which I've assigned. So therefore the electronic configuration of zinc is going to be assigned as argon, and then we shall have the 4s2, and then the 3d10 given as such. So that is going to go in that particular order. So we shall have the configuration for zinc, and then we shall have the configuration for cadmium given as krypton. So krypton is going to have of course atomic number of 36. So we need to have 48. So there's a difference of 10 electrons whereby they're going to be filled by the 5s orbital, which is going to have 2 electrons, and then we shall have the 4d orbital, which is going to have 10. The last layer given this one for mercury, so it's going to have 80, an atomic number of 80. So its configuration is going to be consisting of this particular xenon, and then we shall have the remaining. So there's a difference between 80 and 54, which is basically 26. So the 26 electrons are going to be filled using the 6s2 orbital, and then the 4f14 orbital, and then lastly the 5d10 orbital. So in this case, this is going to be using the various rules which I've mentioned in summary form. These are going to be the electronic configuration of these 3 specific elements which I've listed on the board. Now, the essence for us to identify is that these specific elements are going to consist of electrons, the last electrons occupying this specific, of course, shells. And of course, we're going to look at our previous definition, which we had given basically for transition elements, and try to see whether they are either going to be falling under the category of transition or elements or not. So in this case, if I may just have this one, so perhaps I just wrap this one and just keep this information for us to use in our discussion. So we're going to have this one given as argon 4s2 3d10, and then we shall have cadmium given as krypton 5s2, and then we're going to have 4d10, and then we're going to have mercury given as x6s2 4f14, and then 5d10 given as such. So this information that you have obtained, of course, is going to assist us in trying to identify the specific definition which we are going to assign to transition elements according to the IUPAC system, and of course the common naming system, and of course that's going to assist us distinguish between the two. So for an element to be regarded as a transition element, I've mentioned the concept of the D and F subshells, but in this particular case, elements are elements that contain D and F, D or F. So these are elements that contain D or F, of course, shells, either in the elemental form or in any of their occurring state, oxidation state. So if an element consists of the D or F shell in their elemental form or in their commonly occurring oxidation state, regarded as a transition element. But there is a difference. An element that consists of a D or F shell, either in their elemental form or in their commonly occurring oxidation state, being assigned as a transition element. But according to the IUPAC naming or IUPAC system, an element is regarded as a transition element as if it contains a partially filled D or F. So if it consists of a partially filled D or F subshells, or can give rise to partially filled or D subshells. So I've just given these specific elements intentionally. So in this case, if we try to look at these specific elements, so for zinc, it's going to have S. But since we have said that any element that's going to constitute over the D subshell, then therefore can be classified as in that specific of course shells, it's going to be classified as a transition element. So we have said that if an element consists of the D or F subshell, then according to the general definition, if we were to look at these three specific elements, then therefore they are going to fall under the category of the transition elements. But if you consider the IUPAC system, there's this specific wording of a partially filled D or F subshell. So if we look at this specific configuration for the three elements, we're going to have the D subshell filled for the mercury and the F subshell filled for mercury. So this is going to violate this partial filling over the electrons since these ones are going to be fully occupied. So according to the IUPAC system, this is going to be failing this specific definition, and therefore it cannot be regarded as a transition element according to the IUPAC system. So if we look at cadmium as well, this is going to be having the D, of course, D subshell, just as we have defined for both the IUPAC system and the general one. But in this case, also this is going to be filled. So this is going to be having, so the range of electrons from the first one to the 91, these are partially filled. But if it's 10 electrons for the 5 orbitals or D orbitals which are fully filled, then therefore it's going to violate the second one. So as well, cadmium, according to the IUPAC system, is going to be failing on that specific definition. And if you consider zinc as well, it's going to be falling under that specific category, consisting of the D subshell, but that one is fully filled. So in this particular case, we're going to look at this specific two particular definition of the transition elements as we come across them in our various discussions. But of course, we are going to be emphasizing on their various characteristics and some of the, of course, oxidation states and the periodic trends which we had mentioned, which they are going to be displaying. So kindly videos, and of course subscribe and engage us in the comment section so that we are going to have a healthy discussion on various topics in maths and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.